So maybe you remember, well, I'm sure you do remember this thing about when they went to the moon and dropped a feather and a hammer and they both hit the ground at the same time. Um, and this is because, well, on the moon there's no air resistance because there are no particles. I'm not a scientist, I don't know the exact specifics of it, but there's no air resistance there because there's no particles in the air, etc. And what this showed was that with no air resistance, then the acceleration of these objects was the same, regardless of the mass, because the mass and the shape of the objects is what affects the air resistance calculation. So if there is none of that, then the shape and the mass doesn't particularly have any effect. And on Earth, our downwards acceleration under gravity is 9.8 meters per second squared. It's important if you are studying physics or some other subjects that use gravity. In maths we use 9.8. Other subjects possibly use 10 or 9.81, but in maths it's going to always be 9.8, and you would be penalised if you don't use the value of 9.8. And then because we are calculating with a rounded figure to two significant figures, that means we can only give our answers if using gravity in our calculation to two significant figures. And we'll see that in all of the examples we're going to do. But that's a really key point down here, this section here. You must give your calculations that you have used gravity in to two significant figures, because we can't trust our calculations past the accuracy of the numbers we're using. So, example 1. You'll have found with the first two parts of this Suvat, part of chapter 9, that they give you a lot of information. And you're probably looking at this question and thinking they haven't really told me anything. They've just told me a book falls off the top of a bookcase and it's 1.4 meters above the ground. We know with Suvats we're trying to find some information to fill out in here, but it seems they've only given us one piece of information. You'll find that a lot in this part of the chapter, and you have to learn some kind of key parts that they tell you in questions, and you need to translate that into actual information. So the first part of this question is important to just draw a quick diagram. So if I just draw a quick diagram of what's happening, we've got our book, and I'm going to model that as a particle. That's going to take away any of the air resistance or rotational forces. And it's 1.4 meters above the ground, so 1.4 meters, and this is my ground. And it's going to fall like so, down to the ground. I'm going to label a few things on. Well, it's moving freely under gravity, and that's the whole point of this chapter. There's no air resistance, it's just down to gravity. So in fact, its acceleration will just be gravity. It's important as well to state which direction we mean is positive. When we've been doing it on a left and right 2D motion, we've not had to specify what we mean, because we know right would mean positive and left would mean negative, because they set up all the questions like this. But we'll see in some of the example next where we might want to state the positive direction as up, and if gravity is pointing downwards, so if we state the positive direction is down, then gravity is just a positive value. For it to reach the floor, well, for part A, we are going to have t as our unknown, and it's 1.4 meters above the ground, so we're looking for when the displacement is 1.4, and it's going to be a positive 1.4 because it's going 1.4 meters down, and we've said that down is our positive direction. We need one more piece of information in here. The book falls off. Well, if something's just falling, it's going to fall from a standing start, so the initial velocity is going to be 0. And in this case, for part A, we don't have or we don't need to know anything about the final velocity to answer this. So thinking to our SUVAT equations, we've got all 5 of them now. So you have these in front of you for the exam, so you should have them in front of you now and get to learn them. But for this, we're going to be using S equals to UT plus half AT squared. This is the one that doesn't include V. Substituting in the values I've got here, 1.4 equals to a half 9.8 T squared. 0 times T would just get rid of this factor here. And then when I go to expand that, I can divide by 4.9 and then square root. So here I'm going to get T equals to 0.534 ... We don't need to take into account the negative value of this because we know we can't have a negative value of time. You would generally have a positive and a negative value by square rooting. And then the final bit is we need to say, well, this is actually just 0.53 seconds, and that is to 2 significant figures, and that is because we've used gravity in this calculation. Now trying to find out the speed that it hits the ground, well, I'm going to draw another SUVAT notation out on the side, and we're still taking down as positive. Same diagram, so I'm not going to draw that again. We know the gravity is still 9.8. We know the distance is 1.4. We know it's starting from 0, and we've just found out the time is 0.53, and we're wanting to find this. Always avoid using the value you've just found. And 2 reasons for that. 1, we've rounded it to 2 significant figures, so it's not as accurate as it could be. And 2, we could have got it wrong. And if you get it wrong and then use it in your next calculation, you will get this next answer wrong. Sometimes you're forced to do it, but in this case we have the information, so I'm actually not going to use this. I'm going to use S, U, V and A because these are values they've given me, so I can't go wrong with these numbers. So using, this time it's going to be using V squared equals to U squared plus 2AS, and when I substitute in the values I've got, U squared is 0, so this is just going to be 2 times 1.4 times 9.8. That means V squared equals to 27.44. V equals to 5.238. Again, we aren't going to take the negative version of this because we've said downwards is positive, and it's very clear this is going to be moving downwards. So it is going to be that positive velocity there. And then the final bit, we need to say, well, that's just 5.2 meters per second, and that is rounded to 2 significant figures. This next example. Ball is projected vertically upwards from a point which is 7 meters above the ground with a speed of 21 meters per second. So first of all, let's just get a quick diagram drawn for this, and this is the first thing you should do with all these questions. So we've got our ball here. It's being projected upwards, and when it does that, it's going to move back down like so. Just imagine you throwing a ball. It's going to form a nice quadratic and then return to the ground. So if this is my ground level, they've told me that I'm 7 meters above the ground, and I'm being projected with an initial velocity of 21. The one thing I want to label on here again is my gravity pointing downwards. It's always good to label stuff on here, then you don't end up forgetting it. So let's set up the SUVAT equations here. One thing we haven't done yet is state which direction is positive. And the way I always do it, the way the object initially moves, I find it easier to label that as positive. So from here we can see the ball is initially moving upwards, so I'm going to label upwards as my positive direction. and we'll see what happens to some of the values because of that. So for part A, we're trying to find the greatest height above the ground it reaches. So we're actually trying to find how high it gets here. So what that value is. So we're wanting to find its displacement. The initial velocity is positive 21 because we said upwards is positive, it's being projected upwards. The gravity this time, it's not going to be 9.8, it's going to be negative 9.8. And that is because gravity acts downwards. We've said upwards is positive. So that's how this notation affects that value. And then we're not really going to use the time for this one. We will for the next one, but not for this. So we need to know some information about the final velocity. Well, if you imagine something being thrown up, the point that it's at its highest value, it momentarily stops because it's going from an upwards motion to then stopping, then to a downwards motion. So actually, at its greatest height, the final velocity is always equal to 0, and that's another key thing that they will tell you in these questions, but not tell you so explicitly that where they say the final velocity is 0. They will say the greatest height above the ground. You need to know that, well, at the greatest height, the ball is going to, or the object is going to stop very momentarily and then change direction. You've got to stop to change direction, haven't you? So that's a key bit of information for filling out the value of v. So now we've got this, we're going to see which Suvat equation we're going to use. That's going to be v squared equals u squared plus 2as. V squared is 0, u squared is 21 squared, and plus 2 times a times s. So we're going to get 21 squared is 441. This is minus, because we've got minus 9.8 here, minus 19.6 s. Make sure your s doesn't look like a 5 like mine always do. I'm going to add the 19.6 s to the other side, and then I'm going to divide by it. So 22.5 meters. Two things we need to do. First thing, well, actually what we've found is this value from its starting point to where it's reached at the top of that peak. We also need to include that 7 meters it started above the ground. So actually, the greatest height equals to 22.5 plus 7, and that's going to be 29.5 meters. Final thing we need to actually do is to say, well, really, we have used gravity in our calculation, so we need to say 30 meters to two significant figures. That's just rounding that to two significant figures. Let's have a look at part B then. The time of the flight of the ball, again, I'm still going to label upwards as positive. Okay, so this is where it gets somewhat harder, and taking your time on setting up these values is really important. If we want it to hit the ground, it's all the way over there and it gets to this stage. So actually the displacement for when it hits the ground is 7 meters downwards from where it starts. We don't really care about the total journey it's made over here, because once it's gone up and then reached this point, its displacement is 0 because it's got back to where it started. I've drawn the diagram going a bit outwards, but actually in real life we're talking about it going straight up, straight down, because we can only do these in one-dimensional motions. So it is going straight up, straight down. Just for the ease of this diagram, I draw it a little bit two-dimensional. So when it hits the ground, it is just 7 meters down. So in fact, the displacement is minus 7 because it's 7 against my positive direction labelled. The initial velocity is still 21. We don't care about the final velocity this time. That's not going to help us find the time. The acceleration is still minus 9.8 because we're saying up is positive. Gravity is going downwards. And we're wanting to find the time. So for this, we're going to be using S equals to UT plus half AT squared, the one that doesn't include V. And I know it seems a bit daft having to write this using that each time, but you actually do get a mark for picking the right formula. So write it down, get your mark. So let's sub in my values. Minus 7 equals to 21 T, and this will be minus 4.9 T squared. I've just done minus, I've done a half times minus 9.8. I'm going to get this equal to 0 so I can solve it. So I've added 4.9 T squared and subtracted 21T. I'm just going to use the quadratic formula on here. And if you've got one of them fancy calculators, go ahead and chuck this into your equation solver with 4.9 as the value of A, minus 21 as the value of B, and minus 7 as the value of C. It'll do it for you. So here I'm going to get two values. These three. So I'm going to get 4.5965 seconds, or minus 0.3103. Well, the reason we're going to get a minus in there is because, again, we're solving a quadratic, and the quadratic doesn't understand the question we're modelling. It is just a quadratic. So the minus 0.3 is actually this value down here, if we were to go back in time, and the 4.5965 is there. We just need to make a statement here, just the obvious statement. Well, this is not valid because we can't have that negative value for time. You need to make some effort. It doesn't have to be a big sentence. You just have to make some effort of showing that we don't want that. You can't just write out this value and go for it. You need to show that you've got two values and you've excluded one with correct reasoning. And something as simple as that is all you need. So then therefore we can say, well, our value of time is 4.6 seconds because it's two significant figures. We've used gravity. So it takes 4.6 seconds for this ball to get shot upwards, come all the way back down, and then hit the ground. And final type of commonly seen question is this one, and this is a little bit harder. So a ball is projected vertically upwards from ground level. So let's draw this diagram out. So it's going up and it's going to reach back down to ground level. It's being shot up at an initial velocity of 20. So we'll say u equals to 20 there. It's moving freely under gravity. It always is with these questions where you're going up or down. And we want to determine the amount of time the ball is at least 10 meters above the ground level. So judging off that wording, that's not going to be my maximum height. So 10 meters is going to be somewhere like this. So let's label that on. This dotted line there is going to be about 10 meters above the ground. And we want to find the time that it is on this yellow track. So flying above that. So let's go ahead and figure that one out. So let's get our SUVAT labelled. And we also need to state a positive direction. Again, because we're initially going upwards, I'm going to state positive as upwards. It's just the way I like to do it. I think it's easier. If you did it the other way around, it would be okay as long as you were still consistent on your numbers. So we know initial velocity of 20, gravity of minus 9.8. We're considering the amount of time, so we're going to want to find that. And 10 meters above the ground, so a displacement of 10. And we don't care about this. So we've got our values there. So using s equals to ut plus half at squared seems a popular one with these questions. And I'm just going to fill in my values. I'm going to add 4.9 t squared to the other side. I'm going to take 20t, and I'm still going to get that positive 10. Solve this quadratic, either with the quadratic formula or in your calculator if you've got one of them. And when we do that, we're going to get t equals to 0.5034 and t equals to 3.4983. Now let's just stop and think what that actually means. Well, that means that at this point here, where it is 10 meters above the ground, that is my first value of time. So this one. And then this here is my second value of time. So the time it's above that is the time between roughly 0.5 seconds and roughly 3.5 seconds. So to find the time above 10 meters, we need to do the times subtracted from each other. That's going to tell us how much time it's gone on this yellow track I drew earlier. And that is going to be straight away rounded to two significant figures, 2.9 seconds. And that's the time above 10 meters. So just to recap the key things here. So the key things on these three examples, see if I can squeeze them in here. So key thing number 1, gravity equals to 9.8. Key thing number 2, state a positive direction on your diagram, and then be consistent with your units. If something's going down and you said positive is up, that needs to be a negative. Important thing number 3 that we saw on example 2 is that at max height, at a maximum height, the final velocity equals to 0 because it has to stop to change direction. And then the fourth one, did we have a fourth one? I don't think so. I think that was that. If you can remember that, the other one, I'm looking back through the examples. If you can remember that other one, feel free to add it into your notes. But they're the few for me that are really important. Oh, and the most important one is to draw a diagram and draw a big one. You get like 2 pages in an exam to answer this question. Really, it takes 5 to 6 lines of work in if you do it correct first time. Your diagram can take up half a page. You don't even need the other half page. You don't need the other page and a half to answer this. So don't be drawing an itsy bitsy diagram where you can't see what's going on. If anything, mine wasn't big enough. I was just considering space on my slide. But okay, that's that. If you fancy tackling this exam question, feel free. You can pause it. I'm just going to reveal the answer in a second. Okay, so there are answers. T equals to 2.8 seconds, and then roughly 17.7 for the height. So you can read through them and see if you can make any sense from the mark scheme. I'll let you know if your task on Show My Homework. If there's any questions, shoot me an email or something. Alright, cheers.